when they say use the first derivative test to find local extrema, they mean they want you to find critical points. So you can take a derivative and set it equal to 0. That's the process of finding a critical point. So there's our derivative. I'll set it equal to 0, and it's quadratic, so we'll solve it by factoring. And we solve quadratics by factoring out what we can. We can factor out a 6x from both of those. That leaves us with negative x plus 2 here. And then our goal is to set each factored piece equal to 0. So if you set this equal to 0, then you get x equals 0. And if you set this equal to 0, then you get x equals 2. Those are the two places where we have critical points. Remember, critical points are also where the derivative fails to exist, like when you have a derivative and there's a possibility for a divide by 0 error, but that's not the case in this problem. So those are our two critical points, but remember, we don't know critical points whether they are definitely maxes or mins. We have to test them out. So we'll test points between the critical points to the left of this critical point and to the right of this critical point. Because critical points tell you all the places where you could potentially switch directions. So if you just test one number to the left of x equals 0, like I'm doing here, like with x equals -1, then we can be assured that everything else will be going in the same direction because there's no other critical points. So if I plug in -1 back into the original function, that's going to be a positive 2 for this term. And then plus 6 makes 8. 8 minus 3 makes 5. And if I plug in 0 into the original function, I get -3. Kind of made it too small, but that's y equals -3. And then if I plug in 2 into this function, 2 to the third times a -2, so that's -16. And so that's 2 squared is 4, 6 plus the 24. And then subtract the 3, so I got y equals 5 over here. And then we still, these are critical points, I'll underline them. We still need to test something to the right of our rightmost critical point, so we'll try x equals 4, just so I'm further away. So if I plug in 4 cubed times a -2 makes -128, and then 6 times 16, subtract 3, so I get -35. Holy cow, this function drops like a rock, huh? Unless I did something wrong here. Let me just double check. Yep, okay. It looks like I got what the book is about to get. So let's check out this critical point first. At x equals 0, we have y equals -3. To the left and to the right, we have bigger numbers. That means this is a local minimum. 0, -3 is a local minimum for this function. Okay. And then this is our other critical point. If you look at the values to the left and to the right, they're both below 5. So that means x equals 2 is a maximum because the numbers to the left and to the right drop. So we hit a maximum at x equals 2. Okay, that one was easier because the derivative on this one's just a little bit harder. We need the product rule because we have two different functions of x multiplying to each other. So it's the derivative of the first function times the second function kept the same, plus the first function kept the same, so x, times the derivative of the second function. So that 1/2 comes down and multiplies. And then it gets reduced by 1, so now it's a -1/2, right? Because 1/2 minus 1 makes -1/2. But I'm not done with that derivative of the second function. It's -2x for the innermost function because I need the chain rule, right? The derivative of this is, -2x. So if we clean that up a little bit, that's a negative times a positive. I'm going to change that to a minus sign out front. 1/2 times 2 makes 1. X times x makes x squared. And then I'm going to make this a positive 1/2 by putting it on the bottom. But a square root is the same thing as a 1/2 power. So there it is, all cleaned up. Now we set it equal to 0. And to get x by itself, well, actually first, remember critical points are where the derivative fails to exist. And I made this problem up, so let me check. It's similar to question 5. No, we'll leave it. We'll leave it like this, okay? So we're setting it equal to 0, and we want to note places where the derivative fails to exist because those are critical points, right? The derivative fails to exist if we divide by 0. So the derivative fails to exist if this becomes a true statement. Okay, so we square both sides. We subtract that 27 from both sides, divide a negative sign from both sides, and then we take a square root to cancel out a squared. So there's two numbers, positive or negative square root of 27, where the derivative fails to exist. So we got 2 critical points already. We got a lot to test here. We also need to find the critical points where the derivative equals 0, not just where it fails to exist. So we want to multiply both sides by the square root of 27 minus x squared. Okay, because our first goal should be to get x out of the denominator, so that makes these cancel out. But when I multiply it over here, it's a square root times a square root, so that just makes a power of 1. So the square root is gone on this term. Okay, the square root of 27 minus x squared times square root of 27 minus x squared makes this. And then we're still trying to get x by itself, so subtract that 27 from both sides. Divide that negative 2 from both sides. Now you take a square root to cancel out a squared again, so this is positive or negative square root of 27 over 2 for x. Okay, so 4 critical points. A little bit brutal to check, which, you know, if you don't have to check, maybe you could just use a Desmos calculator. But if you're on an exam and if you're on an exam and you don't have a calculator, then you got to remember this step. You got to have at least the practice, right? Where we got a number line, square root of 27. We'll put that over here. Negative square root of 27. Put that over here. Then square root of 27 over 2. That's halfway between, right? It's negative. This is positive square root of 27 over 2. So those are the 4 critical points we want to check. But let's check out Desmos. Okay, so I've graphed this in Desmos. And then the negative 3.647, that's the square root of 27 over 2. Right? In other words, the square root of 13.5. So the first derivative test, it told us where the potential maxes and mins are. And if we were to make the number line and checkpoints to the left and to the right, we'd find that the negative square root of 27 over 2 is a minimum, and the positive square root of 27 over 2 is a maximum.